Here is another important oxidation reaction for the MCAT exam. Here we have O3. O3 is ozone, and therefore this type of oxidation reaction is called ozonolysis. Once again, the mechanism does not need to be memorized, but what you need to know are the expected products, because this is a common MCAT question. So here we have a particular compound, and if we had to name it, we'd say 1, 2, 3, 4 carbons in the longest chain, and it would be 2-butene, and there's a methyl group at the second carbon, so we would call this 2-methyl-2-butene, and this is plus ozone, and in the reaction mechanism there's also a reducing agent which is used. When ozone is applied to a double bond, ozone breaks the bond and applies oxygens on each side of the bond. In other words, this becomes CH3 carbon double bonded to oxygen to hydrogen. Then we have oxygen double bonded to carbon, CH3 CH3. In other words, just take a look at this chemical as it stands. This is broken, and then an oxygen is inserted for both carbons, and these are separate chemicals. So you see that this is the same carbon, CH3, CH3, hydrogen, hydrogen. There's an oxygen now at the double bond. Oxygen at the double bond here to the carbon, CH3, CH3. That's all you need to memorize, is that in ozonolysis, it is as if it breaks the double bond, places oxygens on either side for both of the chemicals. The way that they like to play with this on the MCAT exam is that they would show you the original chemical, say it's an ozone reaction, and ask you what the possible products are, but they will not necessarily line up the product exactly like this so that you can just look at the original product and see that it just follows perfect geometry. No, what they would do is they would take one of these chemicals at least and just turn it around. It is the identical chemical, but they just take one and turn it around so that you have to use at least your imagination for 2 steps. One step, which is to insert the oxygens and separate, and then you have to look for a product that looks like what you created, but sometimes that means that you have to turn or twist or whatever, and in order to find the actual product. We will now look at more reduction oxidation reactions. Here is a very important redox series. First of all, up here we have a organic chemical. This is clearly an alcohol with the OH group. This group clearly is an aldehyde because it has carbon double bonds to oxygen, and this is to a hydrogen. And this is clearly an acid because we have a carbon to an OH group and carbon double bonded to the oxygen. So this is a series of redox. And thinking about one of the ways that you can memorize oxidation and reduction in terms of organic chemistry, that oxidation is like adding oxygens or losing hydrogens. For example, so we have this carbon has 2 hydrogens attached to it, and there is a single bond to the oxygen. So we go up here, and this carbon has 1 hydrogen attached, so it lost a hydrogen. So it's being oxidized because it loses hydrogens, and it gains an oxygen because here it only had a single bond to the oxygen. Now it has a double bond to the oxygen. So this is further oxidized as compared to this compound. Here we have 1 hydrogen attached to the carbon. Here we have no hydrogens attached to the carbon, so we lost a hydrogen again, further oxidized. Here we have one oxygen attached to the carbon. Here we have 2 oxygens attached to the carbon, further oxidized once again. Then going in reverse, we see that going from here to here, it's as if you added hydrogen to this, you made water, it fell off, Then you added a second hydrogen to attach to the carbon. You made the aldehyde. Let's say we continue to add hydrogens. We add another hydrogen, it goes to this, we form an OH group. Then we add another hydrogen to this carbon, so it's CH2. Then we get back to this compound. So some students like to memorize it as adding hydrogens is going to be reduction. Adding oxygens or losing hydrogens, that is oxidation. Now in terms of the compounds that will permit us to do this, if you wanted to just do a mild oxidation, so you're going in this direction and it's a mild oxidation, then you would use CrO3, which is a compound which I've already mentioned. So this is a mild oxidation, or you can use KMnO4 under very mild conditions just to do mild oxidation. But if you wanted to do a great big oxidation and you wanted to go straight from the alcohol to the acid, well then you would use KMnO4 but under abrasive conditions. That will allow you to go straight on up to the acid. Now if you wanted to do the reverse, you wanted to add hydrogens or reduce these compounds. Well, if you wanted to do a mild reduction, you would use a mild reducing agent like NaBH4. NaBH4 is sodium borohydride. Now you may remember from general chemistry that a hydride is an unusual substance because it's the exception to the rule of all hydrogens have an oxidation number of +1. In a hydride, the oxidation number for hydrogen is -1, and that's exceptional. So you can imagine that just in theory, if you had a -1 hydrogen, a hydrogen that had a -1 charge, that would be extremely attracted to the delta positive carbon, and therefore that negative hydrogen would be attracted to the carbon and it would hit this carbon, and theoretically another hydrogen can fall off as water, and then you would have a hydrogen attached to the carbon producing the aldehyde. So a mild reducing agent is sodium borohydride. Don't forget that you don't need to know the mechanism of the reaction for these reducing agents or the oxidation agents. I'm just suggesting some ideas to you that may make it more easy for you to memorize. Now, however, if you wanted to do a great reduction, you wanted to go from the acid all the way up to the alcohol, the opposite of KMnO4, then you need a strong reducing agent, and that agent is lithium aluminum hydride. Lithium, LiAlH4, lithium aluminum hydride, a strong reducing agent. KMnO4, a strong oxidation agent. And sodium borohydride and CrO3, these are milder agents. And KMnO4 can sometimes be used under mild conditions, as we have already seen. Aromatic rings are so stable. You're supposed to ask, how stable are they? Well, aromatic rings are so stable that under abrasive conditions with KMnO4, KMnO4 cannot break the ring. It cannot break the ring, like we saw for the previous example of a cyclical alkene in which KMnO4 broke the ring and created a diacid. Well, with an aromatic ring, KMnO4 cannot break the ring. And so all it can do, even under abrasive conditions, is it can oxidize whatever substituent the compound happens to have. Aromatic rings are so stable that even under radical conditions, and certainly you should immediately recognize this as being radical conditions, and free radicals are very unstable, very reactive substances. Even under radical conditions, the free radical cannot add to the ring. The free radical can, of course, react with whatever substituent is on the ring, but it doesn't add to the ring. So these aromatic compounds, like the benzene ring, are very, very stable. And of course, you need to know what is the reason for their stability. And the reason for their stability is resonance energy. If we were to write the aromatic compound benzene and we were to draw in the double bonds, you would see that there are two equal structures that can be written for the benzene ring. There is no reason why the benzene ring should be one of these structures any more than the other. So these are two equal structures that we can write for this compound. And as we've already seen in general chemistry and also in organic chemistry, that the reality in resonance structures is not that it is resonating between these two possible molecules, but the reality is that there is some sort of molecule in between where the electrons are actually delocalized in the molecule. There is no true double bond. There is no true single bond. The electrons are delocalized in the molecule. By having electrons delocalized in a molecule, it increases the stability of the molecule. And therefore, by having two different resonance structures that we can write for the molecule, it means there's an enhanced stability. And that is why, even under very reactive conditions, the benzene ring is not broken. An aromatic ring is not broken under these particular conditions. So obviously, like an alkene, like the double bond in an alkene, which is the electron-dense center for the alkene, the reactive part of the alkene. If we were to look at the benzene ring, we see that there are electrons. They are delocalized, but there are electrons. So if you had to imagine what type of substance would finally add to this ring, what could we potentially add to an aromatic ring, you would have to have a compound which was extremely desirous to have electrons, and therefore would be so attracted to those electrons that it could finally enter the ring and make a bond. And so something that really wanted electrons, of course, would be defined as an electrophile, something that is electron loving. That is an electrophile. So we would have to generate a powerful, not a normal electrophile, but a powerful electrophile in order to successfully add to an aromatic ring. An example of a powerful electrophile would be the following. Br2, if it were to be added to iron, an iron-based compound like FeBr3, this particular type of compound is equivalent to having Br+. Now, we've already seen that halides are very electronegative. They're in the 7th group in the periodic table. They're towards the right. They're among the most electronegative compounds on the periodic table. And therefore, the idea of generating a bromine with a positive charge is incredible, because it's something it's a compound that likes electrons so much. We always see bromine as being negatively charged, Br-, or it's neutral in a compound, but it's partially negatively charged because it's electronegative and it's drawing electrons to itself. So the idea that you can create a compound that would generate a species that is similar to Br+, that is a tremendous achievement in itself. But the fact that you have this Br+ means that it would be highly desirous of electrons. It would really, really, really want to have electrons. So this would be a super powerful electrophile. So there are certain ways in order to be able to create powerful electrophiles that would indeed add to the ring, and therefore you would have a compound like this added to the ring as a result of creating a powerful electrophile. Now, once we've used powerful electrophiles to add to the ring, some of the interesting parts of the benzene ring or other aromatic rings is what happens afterwards. In other words, once you've added something to a ring, in what way does it affect the activity of the ring? That's what we're going to look at next. We will now look at how substituents affect the reactivity of the ring. Before we start looking at that, I would like to make a note about nomenclature. Normally, when you add a substituent to the ring, the substituent will be at position number 1. So you would name this carbon 1, this one would be 2, 3, 4, 5, 6, and that's how you would number them. However, it's not necessary to do that. There are formal words that can be applied to the various positions. For example, if you have a substituent attached to this carbon, the position which is opposite to the carbon is called the para position. So this is position number 1, 2, 3, 4, which is actually called the para position. The positions on the side, here and here, which are positions number 2 and number 6, those positions are called the ortho position. So those are on the side, those are the ortho positions. And then between the ortho and the para positions are the meta positions here and here. Okay, so let's say that we have an electron donating group which is attached. Now we will look at examples of electron donating groups in a few moments. But first, let's just take for granted that we have a group here that can donate electrons to the ring. So if it can, in theory, donate electrons to the ring, let's look at the potential resonance structures that would occur as a result. So if it were to donate electrons to the ring, bang, it gives electrons to the ring, creates a double bond here, but wait, this already had a double bond at this carbon, so there would be 5 bonds. So clearly, if this creates a double bond here, this bond has to break. So it breaks and it comes out here as electrons. So because this donated electrons to the ring, and because it donated electrons, its charge would therefore be positively charged. It breaks this bond, the electrons pop out here. Now let's say that the electrons want to join into the ring again. And so these electrons start to come back in here to form a double bond in this position. Well, if it were to create a double bond here, this double bond would have to break and these electrons would have to come out, and they would come out in this position. And so on and so forth. So if these electrons were to come back here to try to join the ring here, this bond would have to break and then come out in this position. In other words, if you were to add an electron donating group to the ring, you would have a situation in which here is our electron donating group up here, and then here is our ring. What would happen is that we would have our bonds here, and what we would get is we would have these positions as being partially negative, partially negative, partially negative. Therefore, because they're partially negative, because these are resonance structures that we can write, various resonance structures that we can write as these negative charges are moving in the ring, and therefore they're really delocalized over the ring, and on average the electron negative donating group ends up being delta positive, and then on average these particular positions end up being delta negative. And so what we say is that these positions are the ortho and para positions. Now imagine that you're a strong electrophile. Okay, so this is our electrophile, like Br positive or something like that. You're a strong electrophile and you had to add to the ring. And you had a choice of adding anywhere you wanted to. Where would you preferentially add to the ring? Clearly, you would preferentially add at the positions which have partial negative charges, which would be the ortho-para positions. In other words, when an electron donating group is added to the benzene ring, we say that it activates the ring. It makes the ring more reactive than it was before, and it directs the electrophiles to the ortho and para positions. However, all these things are statistical, and that's important to keep in mind because on the MCAT exam they can play with you on this. Obviously, the position which would be preferable to be added would be the para position, because these compounds, substituents, they have electrons around them, and you can use either the idea of a steric hindrance, or you can use the idea of electron repulsion, electron shell repulsion, and wanting to stay as far away from the other substituent as possible, and therefore the para position would be the most desirable position to add. Then there would be the ortho position, and one might expect that perhaps 70% would add to this position, and perhaps 29% would add to the ortho positions. But indeed, some 1% may add to the meta positions. So a small percentage would add to the meta positions, but it would still occur. So that's important to remember, that even when it activates the ring, even though it's an ortho-para director, when you have an electron donating group, even though these things are all true, organic chemistry is statistical, and therefore if there is a reaction which is logical to occur, even though it's improbable, even though it doesn't happen often, if it's logical to occur, then it would occur. And sometimes on the MCAT exam, they will play on this and say, what are the possible products? And then people will think, oh, ortho-para director, so the possible products must be the ortho and para. And one of the answers is also meta. Well, then that is one of the possible answers, because ortho, para, meta would be possible, though statistically the great majority would be ortho and para. Clearly, this ring is more reactive than just the benzene ring. If you had a benzene ring without the electron donating group, then you wouldn't have these delta negative positions. You would just have the benzene ring and it would be neutral, and you'd have your delocalized electrons. And therefore, the electrophile could add anywhere in any position. There's no reason for it to add in one position any more than another, because there's nothing attached to the ring yet. But if there is something attached to the ring, if it happens to be an electron donating group, then it not only directs to the ortho and para positions, but it activates the ring. It makes the ring more reactive than it would have been had there been nothing attached to the ring. We will now look at what happens with an electron withdrawing group attached to the ring. Here we have the benzene ring, but now there is an electron withdrawing group attached. Let's see what happens. So this electron withdrawing group clearly withdraws electrons to itself. It's pulling electrons to itself. So we can draw a series of resonance structures that will illustrate that point. So if it pulls electrons to itself, it can pull the electrons from this double bond to itself, creating a double bond here. Therefore, its charge will be negatively charged because it pulled electrons to itself. And because this bond went away, the carbon that used to have electrons here has now lost those electrons, so its charge will be a formal positive charge. Because there's a positive charge here, and there are electrons here, then we can imagine that these electrons would be attracted to this positive charge, bond here, creating the double bond in this position, therefore releasing electrons from this position, and then this position becomes positive. Once again, the electrons here would be attracted to this positive charge here at this carbon. These electrons would come down here, bond here, therefore taking away this positive charge, but because it withdrew electrons from up here, this position would become positive. In summary, if we look at our benzene ring, clearly every time I draw a benzene ring it's going to look a little bit different. But anyway, when we draw a benzene ring with our electron withdrawing group at the top, what indeed happens is that overall, because these electrons are really delocalized, it's not as if there's ever really a positive charge here or a positive charge there. These are just different ways we can illustrate what's happening, because these are resonance structures, and therefore it's really delocalization of electrons. Well, this electron withdrawing group will be delta negative, and this position, the ortho position, would be delta positive. This would be delta positive, and then the para position would also be delta positive. This represents what we looked at here on the left. Now imagine, once again, we have our electrophile, our powerful electrophile that wants electrons. where would it preferentially add? Would it like to add at the ortho positions? Certainly not, because we know like charges repel. So it would preferentially add to the meta positions, which is the best of a poor bunch of options. You see, when we had the electron donating group, we actually had the option of delta negative positions. And delta negative positions are very attractive for something that's highly positively charged. But here, we don't have any delta negative positions. So we have positions here which are not any better than just a regular benzene ring that didn't have anything attached to it. So the electrophile can certainly add at these meta positions. But look at these positions, these ortho para positions, how extremely unattractive for something that's positively charged. Obviously, these positions are less attractive than if it was a benzene ring with nothing attached to it. So by having the electron withdrawing group, by pulling electrons away from the ring, it deactivates the ring. It makes the ring less reactive than it would have been had it just been a plain old benzene ring with nothing attached. And so electron withdrawing groups deactivate the ring, electron donating groups activate the ring. And electron donating groups are ortho-para directors, and electron withdrawing groups are meta directors. And once again, it is statistical. The likelihood is the strongest that the electrophile will add at the meta positions, but it does not mean that 100% will add at the meta positions with no addition at the ortho-para positions. Certainly there will be additions at the other positions, but the great majority would be at the meta positions. Now that we've looked at what would happen if we added an electron donating group or an electron withdrawing group to the ring, let us look at examples of electron donating groups and electron withdrawing groups. Now we're going to look at these groups and see whether or not you would categorize them as electron donating groups or electron withdrawing groups. So first, imagine that this group was attached to a benzene ring, and consider what you would regard for these three different groups if they were attached to a benzene ring. You may want to pause now and consider how you would respond. Clearly, oxygen with a negative charge has an extra electron pair ready to donate into the ring. So this has an extra electron pair. It is clearly an electron donating group. Here we have electronegative element up here, and therefore this carbon, as we know, because it's a carbonyl group, this carbon is going to be delta positive. A delta positive carbon clearly cannot be engaged in electron donating, especially when it has an oxygen on the other side withdrawing electrons to itself. So therefore this delta positive carbon is going to do what to electrons? It's going to attract electrons because it's delta positive. So this delta positive carbon would be considered to be an electron withdrawing group, particularly because of the presence of the oxygen up here. And then here we have a delta negative group, and once again, because this is delta negative, it has extra electron pairs, as we know oxygen has, and it can donate that extra electron pair into the ring and in order to serve as an electron donating group. In fact, when you have an OH group attached to the benzene ring, its name is then changed to a phenol. That's Phenol. That's a phenol when the OH group is attached to the benzene ring. And we discussed earlier that one of the considerations you must have in terms of thinking about whether or not something would be a good acid or not is to also look at what the product would be. And if a phenol gives up its hydrogen and has an O- group, well, we just mentioned that could be electron donating as well. And therefore this can donate electrons into the ring with all the resonance structures that we looked at already. And that means by having these resonance structures, it increases stability. Therefore, phenols are much more acidic than one would consider when comparing it to their relative alcohols, because phenols have a ring where it can contribute those lone pair of electrons and create this resonance structure. And that is the reason for the increased acidity of phenol. And of course, that would be a expected MCAT question that would come up from time to time. So now we've looked at many different mechanisms of reactions. We've looked at other types of organic chemistry reactions. And it's all been quite fun, but is it all true? How do we know for sure that the chemicals actually look like what we think they look like, or at least remotely appear to be the way we draw them out to be? And are these mechanisms actually occurring the way we think they are occurring? Well, that is the purpose of spectroscopy. Spectroscopy includes many different techniques in order to more clearly demonstrate what the organic chemical actually looks like. For example, there is a technique called X-ray crystallography. In the technique X-ray crystallography, a sample of whatever organic chemical is purified, then it is crystallized. In its crystalline form, the chemical has a regular array, and therefore you can take X-rays and send the X-rays through it. And of course, we know from physics, X-rays is a form of electromagnetic radiation. And if you send the X-rays through this crystal, then the X-rays will interfere with each other. And again, from physics, you may remember the issue of diffraction and diffraction patterns, as in the Young slit experiment. So these X-rays will interfere with each other and create diffraction patterns. These diffraction patterns are then analyzed. And because of the interference, because you can analyze the data, you would be able to determine what the shape of the chemical must have been in order to create certain patterns. And of course, the most famous organic chemical of all time was discovered in this way, and that is DNA. There was a woman from England who who created all the data through the experiments of X-ray crystallography, and then of course Watson and Crick interpreted the data and was able to determine the shape of DNA. Now, in order to do X-ray crystallography, you need a considerable amount of pure substance. Then a technique developed called infrared spectroscopy. And in infrared spectroscopy, the amount of substance that you require is much less. And here, once again, you take the sample, you send infrared rays through the sample, and then some of these rays will be absorbed by the sample. That would be the absorbance. And some of the rays would go straight through the sample. That would be the transmittance. So you can look at the transmittance, and then you would be able to determine what areas or parts of the infrared spectrum was absorbed by the particular substance. And that provides information regarding functional groups. And that is very important to memorize. And that is that infrared spectroscopy provides information regarding functional groups. And the units in which infrared spectroscopy is calculated, it's called the wave number, and the units is in centimeters to the -1. Now, if you look in the gold standard, it's chapter 14, you will find a list of many different functional groups and exactly what infrared spectroscopy units are associated with those functional groups. And you are responsible, according to the MCAT, to know those different values. Now, just from experience, I can say that there is at least 2 values that you must memorize. And that is the number 1700. And 1700 would be the absorbance for the carbonyl group. So we know, of course, the carbonyl group being C double bond oxygen. The other number to memorize is 3300, and that is the absorbance for the OH group. Now we know in organic chemistry the most common functional groups that we see in chemicals is the carbonyl group and hydroxide. So these definitely are numbers to memorize. The other ones, if you have brain space, if you have the time to memorize these extra functional groups, then you should do so. But these would be the most commonly found on the MCAT exam, and so definitely these ones should be memorized. It should also be kept in mind that these values are approximations. In other words, when there is a carbonyl group, the value might be anywhere from 1600 to 1800, with 1700 being an approximation. And same thing with the OH group, hydroxyl group, it might be 3200 to 3400, in and around those values, with 3300 being an approximation. In other words, these are good values, good approximations to memorize for the MCAT exam. Next, of course, will be nuclear magnetic resonance. Nuclear magnetic resonance is a form of spectroscopy, and what it does is allows us to know the number and types of hydrogens in a substance. I say specifically hydrogens because the NMR for the MCAT exam is proton NMR. In other words, it's an NMR that is only focusing on the numbers and types of hydrogens found in a compound. So we will look at an example of an NMR and we will work out the details. We will now look at the nuclear magnetic resonance for ethanol. So here is ethanol, it's an alcohol, and this is the nuclear magnetic resonance. So this is the graph that we would get after ethanol was analyzed. So we have this graph, we have at 0 a particular peak at 0. Well, that's just the peak for a substance called TMS. And that sort of is the 0 for the graph. So when you see this peak at 0, you just ignore it because it's really the other peaks that need to be analyzed in order to determine or provide us information at least regarding the substance that we are analyzing. So the first thing that we do when we look at an NMR is to look at the number of groups of lines. The other way of saying it is the number of groups of peaks. So that ignoring this peak here, there's a group of peaks here in the graph, there's a group of peaks here, which is actually 1, and then there's a group over here. So there's 1, 2, 3. The number of groups of peaks is equal to the number of environments that hydrogen will be found in. For example, there are 3 groups of peaks here, and then when we look at the chemical, there's 3 places where hydrogen can live. It's either hydrogen is attached to oxygen, that's one place hydrogen can live. Hydrogen can be attached to the carbon in the middle. There happens to be 2 hydrogens attached to the carbon in the middle, but both of those hydrogen share the same environment, meaning that if you're a hydrogen on this carbon, you've got an oxygen to the left and you've got a carbon to the right. So it doesn't matter if you're hydrogen number 1 or hydrogen number 2, you're experiencing the same environment. So those are 2 different environments for hydrogen, and then there's the third environment. You're a hydrogen that lives at the end of the molecule attached to a carbon. And so there are 3 hydrogens in that environment, but that's only one environment. So the 3 groups of lines indicate that there is 3 separate environments for hydrogen to live in. So that's the first thing we do. How many groups of lines? So we've established that. Now what we can do is we look at the number of peaks in each set, and the number of peaks in this part of the curve will be equal to the number of hydrogens in adjacent atoms plus 1. So the number of peaks, you can write down that peaks will be equal to n plus 1, where n is the number of hydrogens in adjacent atoms. For example, over here, there are 4 peaks, 1, 2, 3, 4. So that means that 4 is going to be equal to n plus 1. Therefore, n is going to be equal to 3. So here, n will equal to 3. And that means the number of hydrogens in the adjacent atom to this particular set of hydrogens, the number of hydrogens in the adjacent atom will be 3. Here, the number in the adjacent atom will be 0, because 1 will equal to n plus 1. Here, the number will be 2. The next thing we want to know is the area under the curve. When we look at the area under the curve, there are many ways that this could be calculated. In a worst case scenario, which they would very unlikely have on the MCAT exam, is that this would be placed on graph paper with very fine boxes, and you would have to count the number of boxes underneath the curve. That would be extremely unlikely for them to do that on the MCAT exam, because it would be obviously too mean to do that. Anyway, the more likely things that they can do is that they can put these regression numbers here, and these numbers, what they will do is they indicate to us already the relative area under the curve. That means that the relative area underneath this curve compared to that, is that this is 1 to 2 to 3. There's another way that they can do it, and that's to draw a regression curve above the curve. So to draw another curve. And what they would do is that the other curve would have steps on it. And this would end up going up way up here. But just to give you the idea, there would be steps on the curve above. This would be called a regression curve. And the reason why these steps are placed is that the height on each step would provide us with the relative areas under each curve. So instead of counting boxes, if they did not provide you with these numbers, then they would provide you with these steps, and then you would know that whatever height this step is, that we can regard that as 1 unit. And this step can fit into this step twice. So then it would be 1 to 2. And then this step can fit into this other step 3 times. So then it would be 1 to 3. And then we would be able to write 2 to 1 to 3 exactly as though they originally wrote those numbers. So it's either the height of the regression curve, which is like a series of steps above the main curve, or there will be numbers that will actually be placed there. Now, the relative areas under the curve is very important because it provides us with the relative number of hydrogens in the compound. So the fact that we have 2 to 1 to 3 means that in our compound there is relatively 2 to 1 to 3 hydrogens. And indeed, when we look at the compound ethanol, we see that there's 2 hydrogens here, 1 in this environment and 3 in this environment. We know that there's 3 environments because there's 3 sets of lines. We know that there must be 1 to 2 to 3 hydrogens in these 3 environments because of the relative areas underneath the curves, 1 to 2 to 3. And finally, we can say exactly how many hydrogens there are in the nearest neighbor based on the n value. So we know that wherever there is relatively 2 hydrogens, which clearly is here, its nearest neighbors have a total of 3 hydrogens attached. So you see this carbon here, it has relatively 2 hydrogens. Its nearest neighbor has 3 hydrogens. The place where there is relatively 3 hydrogens would be here. Where there is relatively 3 hydrogens, its nearest neighbor must have n equal to 2 hydrogens. So there's relatively 3 hydrogens, and indeed, its nearest neighbor here has exactly 2 hydrogens. The only thing to remember is that when you have an electronegative group like oxygen or sulfur in the substance, what it does is it serves as a barrier. In other words, it does not permit this hydrogen to know that it has neighbors on the other side, nor does it permit the hydrogens on this side to know that it has neighbors on the other side. You can imagine it as being a barrier. Therefore, the place in the molecule where there is relatively 1 hydrogen, which has to be this hydrogen here, its nearest neighbor has, well, no hydrogens. because as far as this hydrogen is concerned, it has no nearest neighbor with hydrogens. So this seems very clear. Let's look at a completely different example like propane. So propane, we know that to be CH3, CH2, CH3. It's a alkane hydrocarbon with all single bonds and starts with prop, so there are 3 carbons. So this is propane. So the first thing you'd say is, how many environments are there in the molecule? Well, it's either you're a hydrogen in the middle of the molecule or you're a hydrogen at the end of the molecule. After all, if you're a hydrogen over here, you experience the same environment as a hydrogen here. Meaning a hydrogen here, it's next to a CH2 group and there's no electronegative element near it. And here it's the same thing. So we would expect that in our NMR we would have 2 groups of lines. Okay, so then what would be the relative areas underneath these peaks? Well, the relative areas underneath the peaks would give us the relative number of hydrogens. So it's either you're a hydrogen in this environment or you're at the end. So there's 2 hydrogens in this environment. There's 6 hydrogens at the end. So the relative area would be 2 to 6 or 1 to 3. So we know that the relative area underneath the curves, when we write it, there's going to be a 1 and there's going to be a 3 that we can write, or there will be a regression curve above the curve and the relative heights of the steps will be 1 to 3. Then we want to know, well, how many peaks are there underneath the curve? So if you're in this environment, meaning you're at the end of the molecule, your nearest neighbor would have 2 hydrogens. Therefore, there would be 3 peaks. So we have our 3 peaks where there is relatively 3 hydrogens, meaning at the ends of the molecule. Then let us look at the CH2 where we have relatively 1 hydrogen, which means 2 hydrogens. And where we have relatively 1 hydrogen, its nearest neighbor has, there's 3 on the right, there's 3 more hydrogens on the left, so it has 6 hydrogens as nearest neighbors. Therefore, n is going to be 6. Therefore, the number of peaks in this curve would be 7. So there would be 1, 2, 3, 4, 5, 6, 7 peaks on this curve. Obviously, this is, and then at 0 there will be our TMS as our 0. Obviously, this is not drawn to scale, but at least this provides you the idea behind it. How many peaks under the curve, what is the relative areas underneath the curve, and this allows you to, in order to work out simple NMRs, because for the MCAT exam, the NMR is always going to be simple, and if it's more complicated than you were expecting it to be, then it's likely that you can solve the problem by other means, and they're just trying to trick you a little bit. Now, we've already done a review of substitution and elimination reactions. So we're going to do an extra bonus review of these 2 types of reactions only because they're so popular on the MCAT exam. Also, we're going to look at this particular chemical, which is 2-bromobutane, because it is so popular on the MCAT exam. It is a chemical that comes up very often on the test, either this particular chemical or some sort of derivation of it, which is very close to it. The reason why it's so popular is because we can get all the different elimination and substitution reactions occurring with this very chemical. For example, let's say that 2-bromobutane was in solution. One of the things that could happen is that 2-bromobutane can dissolve. It can dissociate. And it could dissociate into the 2-butyl component, meaning the Br falls off, so we have Br negative, and then we would have a positive charge at this particular carbon. That would be called 2-butyl. And so if there was a 2-butyl, then what could happen is that because this is positively charged, it can draw electrons either from the left or from the right. But we saw that if it had the choice to draw electrons from the left or from the right, kicking out a proton, that it would preferably choose from the left in order to have a di-substituted product. So that is one mechanism of reaction which would produce carbon, carbon, double bond, carbon, carbon. Therefore, the bromine would have been eliminated. The hydrogen that was here would have been eliminated. So that would be called an elimination reaction. The rate of the reaction only depended on this substance. So that would be an E1 reaction. So that is an E1 reaction. This would be the major product, the di-substituted product, and the minor product would be the mono-substituted product, also called 1-butene. So this one is called 2-butene, which is the major product. That's the E1 product. Now let's imagine that this was again in solution, but the solution contained a base like KOH or NaOH. So there's some OH minus that's floating around. Well, let's say again that this in solution dissociated. So again, Br minus falls off. We've got a positive charge here. It's 2-butyl. Then, if there's OH minus that's floating around, the OH minus will come in here in a nucleophilic reaction because it's OH minus, it's negatively charged. This is positively charged, so there'd be a great force of attraction, and so the OH minus would come in here and bond to this. So there's another possibility, which would be carbon, 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 then an OH group, or whatever nucleophile happened to be in solution, and then bonded to carbon. So this would be 2-butanol. This product would have occurred by nucleophilic substitution because you started with a bromine group, you ended up with an OH group, so there's been a substitution at the carbon nucleus from Br to OH. So it's nucleophilic substitution. The rate of the reaction would have depended upon the step in which this dissociated. Therefore, the longest step was this dissociating into the 2-butyl group and the bromide anion. So when it dissociated, that took a long time. But if OH minus is in solution and there's a positive charge there, then the reaction would occur very, very quickly. So the rate determining step, the slowest step was the dissociation here. And because that was the slowest step, the rate of the reaction depends upon the first step. Therefore, this is nucleophilic substitution, first order. So this would be SN1. So here are two different types of reactions that can occur with the same compound. Now let's continue. Let's imagine again that there was NaOH in solution. If there was NaOH in solution, well, we can imagine something else occurring as well. Na plus, OH minus seeing this, well, this is delta positive carbon because it's attached to bromine, which is more electronegative, which is towards the right on the periodic table. So this is delta positive. OH minus would be attracted to this. OH minus would come in here, hit this carbon, and knock out the bromine. And therefore, one of the possible products of this reaction would be carbon, 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 then OH group, which would have to come in from behind, backside displacement, meaning that all the molecules will end up being inverted, OH, carbon. So we again have 2-butanol, or a secondary alcohol, as our product. The reaction would have depended on two compounds, the nucleophile coming in and hitting the original compound, and knocking out the bromine. So there's two compounds that are dependent on this reaction. Therefore, this particular rate of reaction mechanism would be called SN2. It's nucleophilic substitution because bromine has been substituted here and OH has replaced it. It's second order because it depended on this and the concentration of KOH or NaOH or whatever nucleophile that was used. Again, let us imagine that we have this compound and we have a strong base. We could have a base like NaOH or KOH, but it would be more clear if we had a big, bulky base. Sort of like what we saw before, potassium tert butoxide, which is a big, bulky base, which would preferably take primary hydrogens away from this compound. And so if we had a big bulky base or a base that was strong enough that could withdraw hydrogens from these positions, either from this carbon or from this carbon, then what would happen is that you would pull off a hydrogen with your strong base, because the strong base wants hydrogens. So you'd pull off your hydrogen, you'd end up with a negative charge here. This is delta positive, so the negative charge would come in here, form a double bond, and knock out the bromine. So here we would have as a product carbon, 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 double bond to carbon. And that would be our final product. So we would have the elimination of the bromine, elimination of a hydrogen here. So therefore, it would be called an elimination reaction. It's second order because it would depend on the original base that was present, the concentration of that, and it would depend on the concentration of this original compound. So this reaction mechanism would be called E2. So here, using the same initial compound, we can get SN1, SN2, E1, or E2 reactions. And you don't have to worry about, oh my goodness, which one will it do? Will it do this more? You don't have to worry about that. The importance is that you understand the mechanisms of these different reactions, because they're going to guide you into one or the other of the reactions, either by saying certain key words, like for example, we know that there's going to be an inverted reaction. If you know there's an inverted reaction, it must have gone through the SN2 mechanism. If you know an alkene was created, you know it must be elimination 1 or 2. And then if you know that, that in the reaction mechanism, a racemic mixture was produced, or a racemate, then you know that it must have occurred via the SN1 mechanism, because as we've seen previously, in the SN1 mechanism, when this dissociates and you have the 2-butyl, the OH group can add to either side. It doesn't matter which side it will end up adding. And as far as it's concerned, it could do so equally. And if it were to do so equally, then it would produce a racemate or a racemic mixture, which we see in SN1 mechanisms. So generally speaking, they will guide you in one way or the other. Of course, if you had NaOH with this reaction, the first thing that you're going to think of is going to be an SN2 reaction. You'll think of OH minus coming in here, hitting the carbon and knocking it out. But all these other mechanisms are also valid reactions, even if NaOH is in the reaction mechanism. And so what happens is there's a certain probability of each occurring. But the important thing is for you to understand at least that these different mechanisms are possible, and to keep your mind open during the problem and to watch and see which direction are they pushing me into, and then you would be able to solve the organic chemistry mechanism.